So today we're going to look at undirected graphs. We're going to look at three data structures that we'll use to store graphs. Then we're going to talk about two traversal algorithms. These are used for searching information or going over the entire graph. So the two algorithms we'll talk about is the depth first search and the breadth first search. Okay. So let's have a look at the slides. Okay, so here's a quick overview of graphs. But before we begin this, let me see, how many people have already finished discrete mathematics?
CS285?
Yes, CS285.
I'm currently taking it, so basically we were in the end.
Okay, you're taking it now. Have you already studied graphs or not yet?
Not yet, doctor.
We're going to study it tomorrow. We're going to start it tomorrow.
Okay, okay then. So then let me go over this. Graphs are a good way of representing information, data. Okay, so right now we're going to talk about a few applications for graphs. What you see in front of you are graphs. Okay, the picture on the right side is a diagram or a graph for metro. Okay, I'm sure you might have seen something like this for the Riyadh metro when it starts operating. Okay, we will see these 6 lines that we have here in Riyadh. So this graph is showing direction, so from one way to another and all the different stops on the way. Okay, on the left side what you see is also a graph structure. So you can see that there is circles which are connected by lines. Okay, so we're going to have a look at formal definitions for this in the next few slides. So remember one thing, the circles are called vertices. One circle is called a vertex. Vertex or vertices are connected through lines, or simply called edges. So the two words that we'll be using a lot during this lecture is edges and vertices. So vertices are the circles. They are connected by edges. A vertex connects to one or more other vertices through one or more different edges. So why study graphs? Graphs have hundreds and thousands of applications. Okay, it's very interesting to study graphs. Traditionally, we have solved many problems using graphs because you're going to study this thing in the future course, CS210, which is algorithms, the different paradigms of algorithms. So there you're going to talk about the existing solutions and how you apply them to problems. Okay, so if a problem comes in, we'll try to map it to a graph-based problem. If it maps perfectly, we already know the solution for it, so it's easier to find solutions for that. So graphs are very well studied, thoroughly studied. There's many solutions available which apply graphs. Okay, let's have a look at a few examples of graphs. This is a graph for the states. Okay, graph for states. So the vertices are the names of the states. They're connected to other vertices through different edges. So here, an edge is represented as a border. Okay, so if a state is connected to another state, then there would be a edge between the two vertices. So think of it like this: if you consider the map of Saudi Arabia, okay, so Saudi Arabia would be a vertex in a circle. It would be connected to its neighbors. So its neighbors would be start from in clockwise order. So we go from Jordan, okay, and then we have Iraq, then you have Kuwait, then Bahrain. Like Bahrain is not directly connected, but there's a bridge, I think, so you can connect. Yeah. and then there's Qatar, UAE, Oman, and Yemen. All right, so all these countries would be in circles or vertices around Saudi Arabia, and they would all be connected through edges. But can I say that Saudi Arabia is connected to, I don't know, let's say Egypt?
No, because there's a barrier, or like you
Okay,
see.
there is no direct connection, but perhaps you have to go from Saudi Arabia to Jordan, and then from Jordan to Egypt. Okay, so it's not a direct connection. You have to go through a different country. Here's another example, another graph. This is the application in biomedical sciences. Okay, it's protein to protein interaction network. Okay, so this is published in Nature Review. Here's another graph. This is a graph of click streams. Okay, click streams. So does somebody know about a click stream? What's a click stream? No?
I guess the number of clicks in a certain web page, certain place.
Okay, I'll give an example. Let's think about Wikipedia. Okay, Wikipedia is a website. So the people who are trying to access Wikipedia, the server stores this information on the device itself. Okay, which person tried to access which page? Right. So as a user, let's say me as a user, I go to Wikipedia, I search for some information. So from that page, I click on another page. From that page, I click on another page. Okay, I go look at different pages. So the web server is recording all of this information. So we call this thing click stream because there's a stream of data. Data keeps coming in. Whenever the user clicks here, there, click, click, click. So we're collecting all of this information. That's called click stream. So here we're showing a map, okay, as a graph of different pages on the same area, same domain, same website. This particular one is for science. Another example, Facebook. I'm sure all of you are familiar with Facebook. It's not a very secure application, but we're using WhatsApp, which is owned by Facebook. So this is Friends of Friends network. Okay, we can represent a network as a graph. So this is also a graph. You can see this thing, people are represented as vertices. A vertex connects to another vertex if there are friends. Okay, so you can see this thing, a friend of a friend. You can find a friend of a friend using this graph. Okay, this is another graph. Again, Facebook friends. This is quite old. I think it's about 10 years old. Now, of course, there's a lot more subscribers, so you'll see more people here. So you can see a friend connecting to another friend. Okay, the dots, the white dots are representing people. If there's lots of them, you'll find a brighter white color. If there's fewer people, okay, you'll find a lighter gray color, which probably is not very visible. And the blue lines are representing the edges. Okay, another example. This is an application of graphs in politics. Okay, politics. So companies usually are connected to each other through different means. For instance, one company would purchase stuff from another company. Okay, they will market their products to another company and so on. So they are all connected together. You'll notice that the biggest connection you see in the middle, okay, and then there's smaller connections and then smaller connections. But sometimes there are some dots which are not very well connected to the rest of the shape of the graph. This means that they're not very well connected. Okay, so they did this study in 2010, how different companies impact the election process in United States. So usually what happens is there are individuals and companies who give money to the two major parties, Democrats and Republicans, and the presidential candidates. So how do they get money? How they are funded? Okay. Usually this is a conflict of interest, and it's a serious issue in democracies. Yeah, and if you don't want to elect people, they're paid for by certain companies. When these people go in power, they will always return back the favor, to these companies. Okay, this is another graph, again from medicine. All right, so this is the social network of heart disease study done in 2000. Okay, here's another graph. This is a graph of the internet. Okay, literally how machines connect to other machines. So if you zoom in, this is not very high resolution image, but if you zoom in, you'll find that a star, something that appears as a star, okay, is basically a server. It's connected to many different machines, each one of them having its own unique IP address. But to connect to the internet, you need to have a unique IP address. Once you connect to the internet, you're going to connect to the nearest server. The server connects you to the ISP, okay, or the cloud, and so on. So the brighter shape that you see in front of you is most likely a cloud. All right, so I've shown you some pictures. Here's a list of a few more examples. This is a huge area. We cannot list all possible applications, but just to give a few ideas in communications, we have telephones, computers connected together. Okay, so vertices would be the unique phone or the computer with their address, and the edge would be a physical connection, either wireless or fiber or some other technique. Circuits, you guys study circuits in CS175. Okay, so circuits, we have gates, we have AND gates, OR gates. They're all connected through cables or wires or connections. Okay, so we have mechanics, finance, transport, computer games, social relationships, you name it. Any problem, it can be represented using a graph. So let's look at some basic definitions, and we're going to go with this until the end of the course, but I think today is the last formal lecture. Graph terminologies. We talked about the vertex, we talked about the edge. Here are a few more definitions. Path. Path is a sequence of vertices connected by edges. Okay, so we can go around from one place to another place in the graph. But cycle means if you start from one position, I go around somehow in the graph and I end up in the same position where I started from. This is called a cycle. Okay, a cycle. But two vertices are connected if there is a path between them. Okay, so two vertices are connected, are considered connected if there's a path between them. One other definition is component. Component is adjacent vertices which are connected through many different edges. So what you see in front of you in the diagram, you have the graph. This graph has three components. Okay, one last definition here is degree. What's a degree? Degree is the number of edges on a vertex. Number of edges on a vertex. So for example, if you look at this particular graph, this graph has three components. So this is one component, this is the second component, this is the third component. Okay, degree. If you look at this particular vertex, it has only one edge. This means the degree of this vertex is 1. The degree of this vertex is going to be 2 because there's 2 edges. The degree for this vertex is going to be 3 because there's 3 edges connected to it. What should be the degree for this one? Can somebody tell me?
5.
5. Okay, degree for this one is 5. Okay, what's the degree for this one?
1.
1.
1 only. Okay, so this is clear. Moving on. All right, these are some graph problems. Okay, problems which are very common in graphs. ST is source to target. Is there a path from one place to another place in the graph? For example, here. Oops. So for example, here, do I have a path from here to here? There's multiple paths. I can go from here to here, then from here to here. I can go from here to here, here, and then here. So there's 2 paths. There could be more paths. I can go from here 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there can be many paths from one source to one target. Another question would be, if I have so many paths, which is the shortest path? So we can count the number of links. So this seems like the shorter path. There's only 1, 2 hops. 1, 2 hops. If I go this way, I have 1, 2, 3 hops. If I go the longer way, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 hops. Okay, it could be even longer if I go like this. So there can be multiple paths. Which one is the shortest path can be determined by some kind of criteria. Okay. Another problem is cycle. Cycle. Is there a cycle in the graph? The cycles are good and bad, but usually we don't want to have cycles because they create problems. So for example, if I start from here, okay, is there a cycle in there? Again, what's the definition of cycle? If I start from here, go around the graph and get back to the same position, this means there's a cycle. Okay, so this looks like there's a cycle. There's at least one cycle. I can go like this. This is one cycle. I can also go like this. Okay, this is another cycle. So there can be many cycles in this particular graph. How about this one? Do you see a cycle here? This particular component. So I can start from here, go like this, and I have a cycle. Okay, it kind of looks like a triangle, but it's a cycle. So, like I said, if you start from one place and end up in the same place, this is called a cycle. There's 2 other definitions for cycles. We have Euler cycle and we have a Hamiltonian cycle. Euler cycle is if there's a cycle that uses each edge exactly once. Okay, we don't use more than once. Hamiltonian cycle is if there's a cycle that uses each vertex exactly once. All right. There's also the issue of connectivity. Okay, connectivity is all the vertices in the graph connected together. So in the particular example that we saw before, okay, our graph had 3 components. Not everything was connected together. By connectivity means that is there a vertex whose removal disconnects the graph? Disconnects means that there's going to be multiple components now. All right. Planarity, isomorphism. So these are some problems that go with graphs. But again, we're not going to talk about any of these in this class. This is the topic for the next course in algorithms. All right. Now let's talk about how do we implement, how do we represent graph. So let's learn a few basics here. Drawing graph does not mean that you have a unique kind of graph. Look at 2 pictures. Okay, we have in front of you. So there's something on the left side, something on the right side. Look carefully. Okay, both of these graphs are exactly the same. But if you look at the picture, they look quite different. So you have to look thoroughly. Look, on the left side, there's a connection from vertex 7 to vertex 8. Okay, on the right side, we've redrawn this graph using a different shape, different kind of illustration, but underneath it is exactly the same. There's a component which contains 9, 10, 11, 12. Vertices 9, 10, 11, 12. On the right side, 9, 10, 11, 12 is a component. It's not connected to the rest of the graph, but it's sitting right there in the middle of it. So what we're trying to say over here is, when you're drawing the graph, it is possible, okay, that you have completely different shapes, but essentially it is the same graph. So what really defines the graph in itself is basically the definition. How many vertices are there for each vertex, how it's connected to other vertices using different edges. So, okay. Look at this particular example. Are these graphs the same? Anyone?
They look the same, but with different components.
Yeah, look at the drawing. It looks exactly the same. The only difference now is the names of the vertices. Like if the name of the vertices is different, these are completely different things. Okay? On the left side, we're using characters. Right side is using integers. So again, the same. The drawings are exactly the same, but these are not the same graphs. They're different graphs. All right. Okay. Another thing to understand is self-loops. So in graph, the ones that we're looking at, these are called undirected graphs because there's no direction. So self-loops are not allowed. Okay, 0 cannot point to itself. Same goes with multiple parallel edges between two vertices. So these are not allowed. Okay, so from 0 to 1, if I want to go to 0 to 1 directly, okay, there's no indirect way, yeah, there's no vertex in between the path. It's not possible to have parallel edges. It should be only one edge. Either there is an edge or there is no edge. There cannot be multiple edges between two vertices. Okay, let's look at our API. When I want to store a graph, how this is going to work. So we can define a graph class, okay, which takes two constructors. The first constructor takes a parameter integer v. V is the number of vertices. Number is a count, number of vertices. The second constructor is taking a input stream parameter. Like, this is optional if you want to go with that, or you can just completely ignore it. We have a method called add edge. So this will be used to add an edge in the graph. Remember, an edge is always between two vertices. So we're providing two vertices, v, small v, and small w. Okay, so these are just two variables, two integers. We're going to have a special data structure, which is going to hold our graph. Okay, we're going to call it adjacency. Adjacency matrix, adjacency list, or edge list. We have two other methods, v and e. These are simply counting how many vertices are there, how many edges are there. Simply return the size. So instead of size, we return two things. Either we return the number of vertices or number of edges. So remember here, so far what we've studied in all the data structures before, most of the things were always linear. And the size of the data was always given in terms of n, where n was a large value. So we always go from 0 to n, or 1 to n. In graphs, there is no n. Okay, we have two dimensions now. We have the vertices and we have the edges. So we cannot represent things in terms of n. We have to use a representation of vertices and edges. Okay. So here's a definition of the degree. Remember what's a degree? A few minutes ago, I told you what's a degree. Anyone?
Is the amount of connected dots or connected?
Okay, number of edges number of edges on a vertex. Okay, number of edges on a vertex. So this simple method is just counting how many edges are there in the vertex. Okay, this is just an example. All right, if I define a graph object, I pass it an input file. It's going to go and read information from the file and process that. Okay, so we can skip this for a second. We'll get back to it. All right, now let's see how do we represent a graph. There's 3 ways to represent the graph, 3 ways to store the graph. In other words, we're going to have 3 data structures for graph representation. The first one is called edge list. Edge list. So it's more like a linked list that contains edges. Remember, to store an edge is always there between 2 vertices. So there's going to be 2 vertices around an edge. Okay, so what you see on the right side is a list that contains nodes. Each node contains 2 values, vertex 1, vertex 2. So the first is 0, 1. This means that there is an edge between 0 and 1. 0, 2, edge between 0 and 2. Edge 0, 5, edge 0, 6. So I can simply say this is a list of edges. Okay, it's a list of edges. Again, an edge is between 2 vertices. So we have to store 2 values. Does it make sense to you? Can we implement this?
Doctor, can you repeat, please?
Okay, so first data structure is edge list. So I have a graph. Let's build a graph here. Okay, this is some graph. Okay, this is some graph. Now, I would like to have a data structure graph. Okay, so we're building an edge list. And what we're going to do is we're going to have edges. So we have an edge from 0 to 1. Okay, we have an edge between 1 and 2. Okay, we have an edge from 2 to 4. We have an edge from 3 to 4. Okay, something missing?
Yes, from 2 to 3.
From 2 to 3. Okay, there you go. So this is called an edge list.
So, Doctor, how is this 2-dimensional?
No, I didn't say it's 2-dimensional. I'm saying we're storing 2 dimensions. We're always looking at 2 things. We're always looking at vertices, and we're always looking at edges. Okay, 2 things. Always we're going to look at 2 things. Previously, we were always talking about in terms of n. Okay, n is like linear, one direction. Grows only in one direction. But here, we're looking at 2 things. So the vertices can grow, and number of edges can also grow.
Doctor, should it be serial, like 0 to 1 and 1 to 2 and 2 to 3?
Good question. Not really. Okay, 0 to 1 means the same as 1 to 0. 2 to 1 is the same as 1 to 2. So I don't have to store 1, 0 and 2, 1 or 4. I don't have to do that.
Okay.
1 edge is enough. 0 to 1 means also 1 to 0. Is this clear?
Doctor,
yeah.
Coding wise, like how we implement it using lists, like linked list.
So edge list is exactly a linked list. Okay, it's a linked list where every node is storing instead of one, we're storing 2 values. Okay, so this is vertex V and vertex W, or whatever you want to call it, 2 vertices. So would this be a good fast data structure? Let's say if I want to ask you, hey, is there an edge between 2 and 3? How would you check?
Oh, 2n ولا n squared.
Remember, there's no n.
We have to go through the whole thing, so
Yes. So again, we're going to represent this thing using V is number of vertices, E number of edges. So we have to go through this list entirely. Okay. So if I want to find, hey, is there an edge between 2 and 3? I'll go and check these two. 2, 3, no. 2, 3, no. 2, 3, no. 2, 3, no. Go all the way until here, and I find it, and I return this. Okay. How long did it take me to find it? That's the number of edges.
In time.
Okay. So
3 times
find an edge took me O of E time. Okay. O of E time. This looks like something new. We always used to say O of n squared. So this is something new, O of E. So here, E is the size of this list. Okay? If I would like to add another edge, let's say make this edge, what should I do?
you want to add an edge?
It's just a linked list. Remember we used to do this?
Yes.
Okay, make a new node, connect it to the head of the list. Okay, and this goes over here. Yeah, so we simply added another edge to this list. Again, if I want to find something, if I want to find an edge, let's say find an edge between 0 and 4. Is there an edge between 0 and 4? So we have to go through this list. 0, 4, no, 0, 4, no, 0, 4, 0, 4, no, we didn't find it. Okay, so worst case scenario to find something in the graph is O of E, big O of E. Again, why E? We don't give n, we're giving E because the size of this is determined by the number of edges, E. Is this clear? Okay, what's the time to add an edge?
Add an edge?
Yeah, how long would it take?
It depends. If it's in the end, always, then it's different.
Adding.
Okay.
At the beginning.
Or in start, or
Yeah, if you insert in the beginning, it's going to be constant time, O of 1, because we're inserting in the beginning.
but if we insert in the middle,
No, we don't say anything like this, no.
okay.
Okay, remember the graph has no middle. There's no starting position, no ending position. There's no middle. A graph is just a graph.
So
Okay.
what if we want to add a new connection, yani, like an outside connection?
What do you mean?
Like we have like 5 and it's like outside the graph, and then you want to add it.
Oh, you mean there's another vertex?
Yes.
Okay, and now you like to add it.
Or
Like
like
this.
add it at the end or like something.
So you'll do the same thing, 0 and 5. Okay, this goes here, and insert this in the beginning.
So even if it was like 3, 5, or like 4,
Doesn't
5.
matter. Doesn't matter. As long as you want to insert something new, it'll just go in the beginning, which means that runtime would be constant.
Oh, 1, okay.
So the size of your list is growing, okay? But if you're inserting in the beginning, the runtime is always constant.
Oh, 1.
But if you want to find something, or if you want to remove something, okay, remove an edge, the runtime would be big O of E. Okay, because you have to go find it and then remove it. So again, I don't want to go into the code for this. We already know this. We studied this in singly linked list. It's kind of similar to singly linked list. So this is our first data structure. Okay, remember this, the runtime for finding something is O of E, removing something O of E, inserting something O of 1 or constant. Let's talk about another data structure now. Remember I told you that we're going to study 3 of them. So this is the first one. Let's have a look at the next one. Okay, this is the second data structure. It's called adjacency matrix. Adjacency matrix. So what we do is we simply create a 2-dimensional array like a matrix. Okay, the size of this array would be determined by the number of vertices in the graph. So number of rows and number of columns must be exactly the same. This is like a square matrix. This matrix only stores zeros and ones, or true false. 0 means there is no edge between the two vertices. 1 means there is an edge between the two vertices. So for example, is there an edge from 0 to 0? You can simply go to the graph. Sorry, you go to row 0, column 0. This is 0 means there is no edge. Row 0, column 1, this means there is an edge. Okay, 1 means there is an edge. So 0 to 1, there is an edge. Is there an edge between 1 and 3? How do we check? Row 3, go to column 3, 0. This means there is no edge. Okay, do you understand how this is working?
Yes, Doctor, it's clear.
Okay, so this appears to be very fast. Okay, remember here we're using lots of memory. I'll come to it in a second. But this appears to be very fast. Here, when I was trying to search for something, let's say I'm searching, is there an edge between 3 and 4? Okay, what's the runtime?
O of E.
O of E, which is slow. Okay, but here, is there an edge between 3 and 4? I can quickly go, it's just an array, 3 and 4, check the value, so the runtime would be constant. Okay, runtime here is constant. We can quickly go and check, either it's 0 or 1. So finding something is really fast. Like, what if I want to add a new edge? Let's say there's a new edge between 8 and 9. So what I will do is I'll go to row 8, column 9, change this thing to 1. Okay, change it to 1. And now we have a new edge. So now even adding an edge is also constant time. Again, if I want to remove something, let's say I want to remove an edge between 7 and 8. So we go to row 8, column 8. Okay, if there's an edge, this one, okay, we go and remove that, make it 0. Instead of removing it, just make it 0. There's no more edge. We deleted that. So this is really fast. Searching for information is constant time. Adding an edge, constant. Removing an edge, constant. Really fast. But now we have two problems here. Okay. The first problem is, we've said in the beginning, 7 to 8 and 8 to 7 is the same thing. Means that we have to maintain both of them. Okay. If there's an edge from 7 to 8, there must also be an edge from 8 to 7. Okay. This means that we have to make a copy for each one of them. It's going to take double the time. But 2 times constant is still constant. Same goes with removal. If you want to remove an edge, you have to find an edge and then go and remove the opposite one. For example, if there's an edge from 1 to 2, there must be an edge from 2 to 1. You have to go and remove both of them. So far, so good?
Yes.
So overall, this seems to be a better data structure. It's faster, but the problem is the cost. How much memory is it taking? Okay, so the amount of memory it's taking is V squared. Do you agree, V squared? Because one side of the matrix is V and the other side is also V, so V times V is V squared. We need V squared entries for the memory. Okay, which is going to make it very memory intensive, and it's going to take lots and lots of space. Do you notice another thing in this little matrix? Do you see more zeros or more ones?
More zeros.
There's a lots of zeros, and zeros are meaningless. Okay, there is no edge. So do we really need to store a no edge? Aren't we wasting space? Yeah?
Yes, we are.
We are wasting space here. Okay, so let's talk about a third data structure, which is an improvement on this. Remember, this one is called adjacency matrix. The next one is called adjacency list. Adjacency list. All right, so this is a mixture of both. We're going to use vertices and we're also going to use edges. We're going to have an array which is going to store the vertices, and then we're going to have lists which are going to store the edges. It kind of looks like the hash table. Okay, And we'll notice that the runtime is also pretty good. So how does this work out? What we're going to do is we're going to create an array of lists. It's an array of lists. The size of this array is exactly the number of vertices. So in this graph, we're starting from 0, we're ending at 12. So the total size of this array is going to be 0 to 12, or 13. Okay? Now, for every edge that is connected to a vertex, we're going to store it in the appropriate linked list. So for example, there's an edge between 7 and 8. So we go to number 7. Okay, we go to number 7 and we create a node over here. And in this node, we're storing only one value, which is the vertex 8. Okay, we store vertex 8. So for 0, 0 has 4 edges. There's an edge from 0 to 1, 0 to 2, 0 to 5, 0 to 6. Okay, so for 3, we have 2 edges. So there must be 3 to 4 and 3 to 5. Okay, so this is the third data structure. It's adjacency list. Now, if I want to add something, if I want to insert a new edge, let's say we want to connect 4 and 9, what do I have to do?
Add in the linked list.
I'll go to linked list for 4 and add a new node over here containing 9. Okay, containing 9. But now the problem is this is a undirected graph, which means that there must be a connection from 9 to 4. So I'll go to 9,
and then add 4.
For 9, and here I'm going to add 4 also. Okay, so inserting an edge means that you have to add 2 values in your adjacency list. So what's the runtime of this data structure? Let's say I want to find some information. What's the runtime for finding information?
Constant.
Oh,
Remember, accessing this array is, of course, it's going to take constant time. Okay, but if you want to find something over here, let's say I'm looking for the 0. So I have to go first to this array. It's going to take me to linked list number 5, and now I search 1, 2, and 3rd. I found this 3rd. I mean, after 3 searches. No, not log. This is not log.
Not log.
Here, if I'm searching for 5, it's going to be 1, 2, 3, 4. Here, if I'm searching for 0, it's going to be 1.
So n minus 1.
Searching for 10 is going to be 1, 2. Okay. So worst case scenario, we're always looking at the big O. Worst case scenario, what's the maximum time it's going to take? Remember a few minutes ago, we studied a property which is called degree. What's the degree for 9?
3. Yes.
Degree is number of connections. Okay, number of connections. So 9's degree is 3. Degree for 10 is 1. Degree for 12 is 2. Okay, so can we say that the maximum time it will take to search an edge is the degree for the vertex? Okay, for example, find an edge on 12. This would be the degree for 12. Yani maximum is 2. Okay, find an edge for 0, starting at 0. That will be degree of 0. So 1, 2, 3, 4. Maximum is 4. Okay? So, all right. Now, in reality, your graphs look like what you see on the left side. Okay, they're mostly sparse. Sparse means that there's lots of blank spaces. Okay, very few edges connect. Very rarely you're going to find very dense graphs like the one you see on the right side. Okay, so overall, if I want to see which is the best data structure, remember we just saw 3 different data structures. We saw an edge list, we saw an adjacency matrix, and we saw adjacency list. So here's a comparison for each one of them. If I want to insert an edge, okay, all of them, their runtime is constant. So inserting an edge is constant. If I want to find, if I want to search, okay, if there's an edge between 2 vertices. So for the edge list, okay, the runtime would be E, which is the maximum possible time, E, number of edges. Adjacency matrix was really cool, it was fast, runtime was constant. But for adjacency list, we can say degree V. Okay, if I want to delete something, so it will be very similar to searching. Okay, so in the edge list, the runtime would be O of E. Adjacency matrix would be O of constant, O of 1, and adjacency list would be degree V. Okay, now how much memory is it taking? Space. So for graphs, space is very important because, you know, here I just showed you. When you're designing your data structure or to store a graph, you have to be very careful with the space because it can take a lot of space. So when it comes to edge list, the space taken would be O of E, okay, which is simply number of edges. For adjacency matrix, the space taken would be V squared because now we're going to store everything in a two-dimensional array. The size of this array would be V times V, yani number of vertices times number of vertices. This is probably the first one. Adjacency list, okay, is going to take E plus V. E plus V. E is the total number of edges plus the number of vertices. So look here, okay, all the edges are stored in the different linked lists, and we have an array which contains the vertices. So it's going to be easily V plus E. Okay, any questions here? Is everything clear?
The last two on the right, degree V,
Yeah.
what does it mean?
Degree is number of connections. See here, I explain it. So, for example, degree.
Oh, yeah, right.
The number of connections for a vertex.
Yes.
Okay, so this is clear. The code is given there. You can have a look at the code. Yeah. Now, let's move on. So we just saw the three data structures. Okay, again, what are the data structures quickly? We have edge list. Okay, we have adjacency matrix, and we have adjacency list. So which one is the fastest for searching?
Adjacent matrix.
Matrix is the fastest for searching. Okay, which one is the most space efficient?
Edge list.
Edge list takes the least amount of space. Okay, but adjacency list, okay, is the most optimal one. It's really fast, and at the same time, it's taking exactly the space needed, not too much, not too little. So overall, this one would be the best data structure. Okay. All right. Now we're moving on. We're going to talk about traversal algorithms. We're going to look at two of them. We're going to see the depth first search and breadth first search. So let's go ahead and have a look at this. Okay. So first of all, a graph has no beginning, no ending. You can start from one place and you can go around it. Okay, there's no end. But usually with traversal, when I say that, okay, start from one place and make sure you visit every single vertex in the graph. Okay, so if I have this kind of condition, this means I am going to visit every vertex at least once. So usually the searching algorithms or the traversal algorithms are a bit slow. Okay, here's an example of a maze. Okay, a maze. I'm sure you played this as a game when you guys were kids. So we can represent a maze as a graph where every intersection could be given as a vertex, and every straight line or a path is given as an edge. So you can see this thing, the left side is a maze, and we can represent this using a graph on the right side. Okay. So here's one approach for traversal. So we can go in a direction. Every time we move to or we jump to the next vertex, we're going to roll a ball of string. Okay, this is going to be there to remember that we came from this path. If I don't remember this, I will be lost and I'll go around and around and around, and it will take a very long time and won't be able to get where I want to get. So this is one approach. Okay, think of it like this, that we have a ball of yarn. Okay, and we can, whenever we jump to the next vertex, we're going to leave a string behind us. So we can keep going around and we can see where we came from. This way it will be easier to traverse through the graph. Okay. First use, I'm sure you guys have studied this in school, the story of the Minotaur. I don't know, did you guys study this or not?
We did.
Minotaur?
It's a fictional Greek story. Usually we teach this to middle school kids for English, I think, English literature, English language. No, never studied this? Okay, anyways,
No.
you can Google it. Okay, the idea is that there was a character and he was put in a maze like this. Okay, and he had to save his life, and there was a monster in there, and he wanted to kill that guy. So what he did was he had a ball of yarn. Wherever he went, he threw the yarn behind him, so he would know where he's going. This way, he traversed through the maze and got out of there safely. Okay, just long story short, but you can go ahead and read it. It's interesting. All right. Another example is a Claude Shannon mouse experiment. Okay, so this guy, he created a maze, and he uses real mice. He will put a piece of cheese in one place, and he will see that how the mouse would traverse through the different passages until it reached the cheese. Okay, so here's a simulation for maze exploration. Okay, so we're going to start from one dot, one red dot, and we want to go to the other red dot. Okay, so look carefully how we're traversing through the graph. So you notice we're going in one direction. Sometimes when we reach a cross section, okay, we decide to go in one direction. Okay, we reach one end. Once you reach an end, you stroll back. Notice the color of the dot is changing because we're reusing this information to go back. Gray means that we have already traversed this and we should not come here again. Okay, so again, if one path is already traversed, we mark it gray, we don't get back to it again. So again, as a person, we know where to go. Okay, we're smart. The computers are not very smart. It's going to probably explore every possible way before it reaches that dot. Okay, there you go, we found it. So again, we did not explore all possible paths here. We just kept going in one direction until we reached a dead end, then we reverted back and looked for the next path, and then keep going in that direction until it was a dead end, and so on, until we reached our destination. So it took a very long time for a maze like this. How about this one? You think it's going to be faster? Okay, the simulation increases speed, but it's still going to take quite a long time. Again, we're looking for the most straightforward path. We go in one direction, keep going until we reach a dead end. Once you reach a dead end, we revert back and look for the next path. So now you can see this thing, as the size of the maze grows bigger, it's going to take longer find paths. How about this one? Okay, I have time to run this simulation here, so let's skip that. Okay, so here's your algorithm for the first approach. This is called the depth first approach. Okay, we go in one direction, we keep going in one direction until we reach a dead end. Once we reach a dead end, we step back and then we try to find another path and then we move on. Okay, so this is the simple algorithm for depth first search. Okay, so how do we implement this? So let's first, I'll go with an example so that things will be clearer. Okay, let's build a tree and then we'll, build a graph and then we'll try to do a DFS on it. Okay, so I'm going to create a graph over here. Okay, so imagine this is some graph. We would like to do a DFS on this, depth first search. It says start at 0, start at 0. So what we're going to do now is let's use our yarn. Okay, the red one is our yarn. So we start at 0, and I write 0. And then we go to the next path. Notice there's only one path. So we go to 1. Okay, so 0 is visited and 1 is visited now. Now from 1, we have 3 options. We can go to 0, we can go to 2, we can go to 4. Notice this is already visited. Should we go back? Yes, no?
No, we don't need to go back.
Yeah, so now we have 2 options. Either you can go with 2 or you can go with 4. So the order needs to be determined. Okay, we can say that, all right, let's pick the smaller value of the vertex, let's say. Okay, let's assume that. So we go to 2. Okay, I'm going to consider 2 in my path now. Okay, once I've reached 2, now I have 2 paths. I can go to 3 and I can go to 6. So if you use the same analogy, go with the smaller one. So we'll go to 3. Okay, we go to 3. And now we've reached 3. From 3, again, we have 2 paths. I can go to 4, and I can go to 5. So we go to 4. Okay, we go to 4. Now from 4, we have only 1 path, which is we can go to 1. But remember, 1 is already visited. Okay, so we're going to go back to 4. Okay, and then from 4, we have only 1 path, which is 3, but 3 is already visited. So we're going backwards. Okay, now we've reached 3. Okay, we came from 2. We shouldn't go back to 2. Next path is 5. Okay, so we'll go to 5. Write 5 over here. From 5, we can go to 8. Go to 8. From 8, there's only 1 path, so we can go to 6. So we go 6. Okay. From 6, again, we have 2 options. We can go to 2 and we can go to 7. So again, our rule says that go to the smaller one. So we'll go to 2, but 2 is already visited now. Okay, so we'll roll back. And then now we go to the other path, which is 7. So we go and visit 7. So again, once you've reached 7, there's nothing else. So we have to go back. Okay, we came from 6. 6 came from 8. 8, we got here from 5 to 3 to 2 to 1 to 0, and we reached the original place where we started from. So this is called a depth first traversal. Okay, is this clear? Any questions about this? So if somebody says start at 0 and give me a DFS for this graph, so this would be the output. Okay, you're going to give this particular order. So 0, 1, 2, 3, 4, 5, 8, 6, 7. That's the order for this graph. Is this clear? Everything is fine?
Yes, it's clear.
I'm going to show you how to implement this. So learning this is very important before we actually go and look at the code and how to implement that. So if this is clear, we can move on.
Yes, doctor.
Doctor, it's very clear, yeah.
Okay, so that's how we implement the DFS, depth first search algorithm. What we're going to do is we're going to create a two-dimensional array like this. Okay, we're going to have rows and we have two columns. So the first column is marked, is just storing 0 or 1. Okay, 0 means not visited, 1 means visited. And the second column is edge 2. Edge 2 is remembering how did we get here. So for example, when I start, let me show you the simulation first. Okay, so here's my graph. I'm going to read up the graph, and we're going to build this little table here, or matrix, whatever you want to call it. So in the beginning, we're going to mark all the marked as false. I mean, nothing is marked. We haven't visited anything yet. So we're going to start at 0. Notice that I've marked 0 as true. Okay. Next, from 0, we go to 6. Okay. Go to 6. So we're going to mark 6 as true. And remember, edge 2 is 0. Okay, how did we get to 6? We came from 0. From 6, we're going to go to 4. Okay, so we're going to mark 4 as true. And edge 2 becomes 6. How did we get to 4? We came from 6. Next is 5. So we go to 5. Okay, edge 2 is 4. We came from 4. We go to 3. Okay, again, it's marked as true. Edge 2 is 5. Okay, from 3, we have two options. We can go to 4 and we can go to 5. So we go to 5. 5 is already visited. We go to 4, already visited. Matter how there's nothing else, we have to roll back. So we go back to the previous node, 5, and now look for other options. So there was two options. Either I can go to 3 or 4 or 0. So 3, we just came from 3. 4, we cannot go to 4. And 0 is also already visited. So now we roll back. Go back to 4. Again, check over options. So 4 can go to 3 and 5. Both of them are visited. They can go to 6, but 6 is also visited. So we're done here. We roll back to 6. Again, from 6, we can go to 4 and we can go to 0. 4 was already done, so we go back to 0. From 0, we can go to, okay, we can go to 2. Visit
And we can go to 1.
We go to 1. Okay. 1, we visit 1. Then we go to 5. And 5 was already visited, so we're done here. Notice that in this particular graph, we started at 0. We cannot possibly reach 7, 8, 9, 10, 11, 12. So they're going to stay as unvisited. Clear?
Yes, doctor, it's clear. But what's the goal
Doctor, I
of
have a question.
You got a first question?
If we went from 0 to 5 in the beginning,
Yeah.
we will still solve it correctly, right?
Yes, the order does not really matter unless they tell you how to go with it.
Okay.
So what I did over here was I said, all right, I'll go with the smaller number. If I have a choice, I'll go with the smaller number. But the one in the slides is random. Okay, whichever comes first, you go to that.
So, doctor?
Yeah.
So the goal is to reach every single possibility?
The goal is to, you start from one place, okay, and then try to visit every possible thing, whatever is reachable. It is possible that you may not reach everything. That's fine.
Okay.
All right. So
what's the point of this whole thing?
Sorry, again?
What's the point of this whole thing that we did?
Graph traversal algorithms are one way of finding out the different possible paths. Okay, if there's a path from here to here. This is one of the examples. There's again many other problems that can be solved, but this is one of the basic, simplest ones.
Okay.
So here's the code for this. Okay, again, I'm not going into much detail here. So you can go ahead and copy paste it. It should work fine in NetBeans. Okay, these are some proofs and properties for that. All right, here's a very common example. I'm sure you guys have heard of Photoshop.
Yes.
So Photoshop, there's an option called flood fill. Okay, sometimes also usable with magic wand in Photoshop. So you can select a color and you can change the color. What it does is it looks at all the adjacent pixels and changes their color. So there's two pictures in front of you, left and right. Left is the original photo. You can see this, the sky seems very polluted. Okay, it does not look very nice. So what we can do is we can put a darker shade of blue so that the sky would look cleaner, nicer, without any smog or pollution. Okay, you can do this thing with a depth first search. How does that work? What we do is we look at the picture. Every single pixel becomes a vertex, and the vertices which are connected together. Okay, of course, each one of them is going to have its neighbors on its 8 sides. Okay, and then we look at the color. If the color is matching in the neighbors, we go and change the color for all the neighbors. So this is what makes it nicer and easier to work. So that's a very simple application of depth first search as a graph. Okay, let's look at the second topic, which is the breadth first search algorithm. Breadth first search algorithm. So let me use the same graph over here to explain how this works. Okay, and then, okay. Or should I draw it again? Okay, I think I better draw it again because it's not going to look very nice here. Okay, so it's just the same graph, just redrawing it. Okay, so let's see what is breadth first search. Or BFS. Okay, what we're going to do is, let's say we start at 0. Okay, start at 0. So what we do is we try to explore all possible options before we move to the next step. Okay, so we're going to start with 0. We visit 0. Okay, it has only one neighbor, so there's no other choice, so we go to 1. Okay, we visit 1 now. Now, 1 has 2 other options. Either we can go to 0, of course, it's already visited. We can go to 2, or we can go to 4. So what we're going to do is we're going to go and visit 2, and then we're going to visit 4. Okay, so we're going like this. We visit every single neighbor before we move on. So here we're going to visit 2, we're going to visit 4. Okay, now we've visited all possible things. Notice we're done with 0, we're done with 1. We've explored all possible neighbors of 0, all possible neighbors of 1. Now let's go and have a look at all possible neighbors of 2. So 2's neighbors are 1, which is already visited, 3, and 6. So I'm going to list 3 and 6 over here. Okay, so 3 and 6 are visited now. So we'll go this way. Okay, now we're going to go and check all possible neighbors of 4. So 4's neighbors were 1 and 3. Both of them have been visited. Okay, 1 and 3, both of them have been visited. So we don't need to list anything else. Then now we go and check the neighbors of 3. Okay, so 3's neighbors are 4 and 5. So 4 is already visited, 5 is not. So we're going to list 5 over here. Okay, so 5 is now visited. We went through it like this. Next, we check the neighbors of 6. Okay, 6 has 3 neighbors now. There's 2, which is already done. And now we have 7 and 8. So we're going to list 7 and 8. Okay, here's 7 and 8. Okay.
Done.
And now we go and check the neighbors. So 7 and 8 are visited. Now we go and check the neighbors for 5. 5 neighbors are 3 and 8. Both of them are visited now. Okay, then we go check 7. Again, 7 has 6 as a neighbor, which is already visited. And then finally 8. And it has neighbors 5 and 6, which are already visited. So there you go. This is the traversal output of traversal, the breadth first search traversal starting at 0. Okay, notice this would be different from the depth first search. Here you're getting 0, 1, 2, 3, 4, 5, and then 8, 6, and 7. Here we're getting 0, 1, 2, 4, 3, 6, 5, 7, and 8. So the order is different. Is this clear? Does it make sense?
Yes, Doctor.
So if you look carefully, we're going like this. We're going in levels. Okay, we go look at this one. Then we did this. Then we did that. Okay, and so on. So we try to explore all possible neighbors options before we move on to the next one. Okay, let me show you the simulation for this. How do we do that? Okay, so this is some graph. Again, we create a similar kind of list. But here, it's better to use the help of a simple queue data structure. So we start at 0. We're going to put that in the queue. We explore its neighbors. Okay, mark 0 as visited. And then we go and explore its neighbors. Its neighbors are 2 and 1 and 5. Okay, so we add all 3 of them in the queue. Next, we go and check the first neighbor, which was 2. Okay, we remove 2 from the queue and explore its neighbors. So now 2's neighbors are 0, which is already visited. 1 is already in the queue. 3, so we add it to the queue. And 4, we add it to the queue. Okay, now we go and remove the next one, which is 1 in the queue. We explore all of its neighbors. Its neighbors are 0 and 2. Both of them were already visited. So we remove the next one from the queue, which is 5. 5's neighbors were 0 and 3. Okay, so 0 and 3 were both visited or in the queue. So we remove 5. Next is 3. So 3's neighbors are 5, 2, and 4. Again, 5 and 2 are visited, and 4 is still in the queue. Okay, and finally we remove 4. Has no more neighbors, so we're done. Okay, so that's how you would visit the graph. Okay, so here's a code for this. Very simple. Okay. So breadth first search goes by the levels, the way I just explained now. Okay. Here are some practical applications for VFS routing. The communication students will be interested in this. So when you want to call a friend who's in a different city or different country, what happens is your call goes from your phone to the nearest antenna, which forwards it to the nearest BST device. Okay, that is going to try to explore all possible paths before it is redirected or rerouted to the next node or the server. Okay. This is also interesting. If you're not familiar with the Oracle of backend, if you're a movies fan, okay, you can use this thing. So the Oracle of backend was a web-based application. It was created about 20 years ago. This is based on the international movies database imdb.com. So if you like an actor and you want to follow his movies and you want to see if this actor worked in certain movie where another actor worked, okay, so you can look at these two and see how they're connected together. Okay, so this is interesting. You can go ahead and try it. It's going to ask you to type the name of two actors, and it will show you the degree of connectivity between the two of them. Okay. This is the Airdus numbers. Here's another example, very interesting.